The fourth thing I want to talk about is this very useful theorem. It's called the Fatou's lemma. You've probably seen it in PMATH 450, and you probably already know it's a really useful theorem. So I'm just going to quickly go through this lemma. It's really simple, pretty much the same thing as you've seen before. So suppose I have a bunch of fn greater than 0. They're measurable. Okay, and not assuming anything about their increasing or decreasing. So the Fatou's lemma is saying the following. So if you want to do the lim-inf of these fn, okay, we prove that this lim-inf is also a measurable function, so this makes sense. And you can actually compare with the lim-inf of the integral, so lim-inf of fn d mu. Well, Fatou's lemma is saying, well, you don't really expect the equality here, but you always have a less than equal sign, okay? So the proof, again, is really, if you've seen it in 450, it's pretty much the same proof. You just change everything onto a more general measure space. So for each of these k, let's define gk to be the infimum of the tail. So infimum of n greater than or equal to k of fn. Okay, so let's define the point wisely first. We saw the infimum of bunch of measurable function is again measurable, so this is certainly measurable. And these gk are non-negative, okay? And you may see that because as k increase, you're taking a infimum over, well, the tail is getting smaller and smaller, right? So you're taking an infimum over a smaller and smaller collection of sets. When you're taking infimum over a bigger set, you get a smaller number, so these gk will be increasing, okay? As you take the smaller tail, you're taking infimum over a smaller collection of numbers. All right, so we're kind of setting ourselves into the condition of MCT, so let's look at the limit of gk. So this is k goes to infinity, so if I write it out, this is the limit when k goes to infinity of the infimum n greater than or equal to k of the fn for x. And you know this is by definition really just the lim-inf, okay? So you should probably know this from, I don't know, your first analysis course. This is the lim-inf of the fn of x, okay? All right, so let's see what the monotone convergence theorem is telling us. So the monotone convergence is saying the integral of this limit of gk, so this is over k, well, which by definition is the lim-inf of the fn d mu over n. Okay, so MCT is telling you can move the limit outside, okay, but remember you're doing the sequence gk, so when you're moving the limit out, you're saying the limit k goes to infinity of this integral gk d mu, okay? So what is gk? Well, gk is the infimum of all the tail beyond this number k, okay? So let's look at how we can reduce this one. So because gk is less than or equals to all the fn when n is greater than or equal to k, so here we have this inequality for all n greater than or equal to k. So we saw the integral is monotone, so the integral of gk d mu is less than or equals to integral of fn d mu for all n greater than or equal to k. Another way of putting this is like, this is essentially less than or equal to the infimum. Okay, so you can take the inf over all of these n greater than or equal to k, and you still have this inequality. Okay, so because of that, so let's keep this in mind. So we have that each of these integral gk is less than or equal to the inf of the tail of this integral. Okay, so this is certainly less than or equals to the limit when k goes to infinity. And you now replace it by the infimum of the tail, which is the integral of fn d mu. And again, you have the limit of the inf, which by definition is the lim-inf. Okay, so let's say n goes to infinity of integral fn d mu. Okay, so Now you connect everything. This is essentially the Fatou's lemma. Okay. All right, so the last thing I want to talk about is that a stronger version of MCT, we can actually only need MCT to hold almost everywhere. So here is the statement. Suppose I have a sequence of measurable functions. Again, let's assume they're non-negative. And let's assume that they're increasing almost everywhere. Essentially is basically the set for each of these n, where the set where fn is greater than fn plus 1 has measure 0. And let's also assume that the limit of these fn converge to f almost everywhere. Okay, so everything in MCT is replaced by the almost everywhere version. Well, then you can actually show that, yeah, the MCT still holds. Okay. So to prove this theorem, we need to prove a little lemma about measurable functions about almost everywhere. Okay, so let's prove the following. So suppose I have some f greater than or equal to 0, again, measurable. Then the integral of this f equals to 0. That's if and only if f is equal to 0 almost everywhere. Okay, so we need this little lemma. Well, the proof is really simple. Let's see the one direction. So let's prove the backward direction. Okay, so let's let E is equals to all the x where the f of x is not equal to 0. Okay, so it has to be strictly greater than 0 because f is non-negative. So if you have a simple function, if you go back to the definition of this integral, then if you have a simple function phi that's sandwiched between 0 and f, well, then what you know is that the phi, if you restrict it to the complement of E, because on E complement, f is equal to 0, so phi has to be equal to 0, okay? So these phi, if you write it, is going to be equal to some alpha I chi of EI, and each of these EI will be contained in E, so their measure has to be equal to 0 because mu of E is equal to 0, okay? So by almost everywhere, we have mu of E is equal to 0. That's basically what does it mean by f equal to 0 almost everywhere. All right, so because of that, you can see that I of I by definition is just alpha I times the mu of EI, where each of this mu of EI is equal to 0. So I of I is equal to 0 for all such phi. Okay, so you take the supremum over such phi, you get the integral. So the integral is also equal to 0. So that's one direction. The other direction is basically use something I put on your assignment 5. So there's this Markov inequality that essentially say that suppose you have consider all the x where fx is greater than 1 over n. Okay, let's put greater than 1 greater than equal to. Then the measure of this set has an upper bound. It's actually bounded above by n times the integral of these f d mu. But n, even though n can be large, the integral is equal to 0. So when you multiply 0, you always get a 0. So in other words, you have this measure where f of x is greater than or equal to 1 over n. This one has measure 0. And now you can see that the f of x not equal to 0 is basically, if it's non-zero, then it has to be greater than one of these 1 over n. So it's a union of these measure 0 sets. Okay. So f of x greater than or equal to 1 over n. This one has measure 0. Oops. All right, so we now prove this little lemma. Now let's go back to prove our almost everywhere version of the MCT. Okay, so proof of the almost everywhere MCT. So let's just take care of all the sets that are causing trouble. So let's let En to be all those x where possibly I have some f of x greater than f of n plus 1. That's where it's not monotone or not monotone increasing. So these En are all measure 0 sets. And I have another set that's called E0. That's where the limit of f is not equals to the limit. Okay, so again, we saw because the limit is almost everywhere, this mu zero, E0 also have mu measure 0. Okay, so let's let E to be the union of these En, where n, let's say, greater than or equal to 0, so include the E0 and all the En. Okay, so again, sigma subadditivity tells you mu of E is equal to 0. Okay, union a bunch of measure 0 sets, you get a measure 0 set. Okay, so but on the E complement, everything is nice. Okay, so on the E complement, you have these Fn that's actually increasing, and the limit of these Fn is equal to F. Okay, that's everything on the E complement. Or another way of putting this is you consider En times chi of E complement. They are positive, they're increasing, and the limit of these sequence Fn, you multiply chi of E complement, that's just F times chi of E complement, okay? So by the usual MCT, what we have is that the integral of these Fn chi of E complement, d mu, that will converge as n goes to infinity to the integral of f E complement d mu. But as you can see, the Fn and these Fn times chi of E complement only differ on the E complement. So we just saw that if you differ by a measured 0 set, it doesn't change your integral. So on either side, you have that's just equals to the integral you expect. Okay, just ignore the chi of the complement. So this limit still holds. Okay, so this proves this almost everywhere version of the MCT.